Hiya, kids! Today's lesson is entitled An Introduction to Solutions. Let's start with a definition. A solution, if you remember from earlier this year, is a homogeneous mixture. A friendly reminder that homogeneous means the components of the ratio of the components of your mixture are uniform or the same throughout. What is it that we're mixing together? We're mixing two new vocabulary words, the solute and the solvent. So another way to define a solution is to say that it's a solute plus a solvent. It's not really mathematical, it's just another way to write the expression. Let's start with a picture, you know me, science teacher, not art teacher, where I'm trying to show you the making of a solution where I have water, and I have a spoon or a scoopula or something along those lines filled with salt. Remember, sodium chloride. And when I dissolve the salt in the water to make salt water, again, the salt water is made by adding the salt to the water. The salt is what's being dissolved. The water is doing the dissolving. To link that up with our vocabulary words, the substance being dissolved, or the salt, that is our solute. And the water, the substance doing the dissolving, is our solvent. One way students like to keep track of this is the V in solvent and the W in water have similar shapes to them. Excuse me. And that's how students remember that water is the solvent. Now, most times, you're right, water is going to be our solvent, and when it is, we call that state of matter aqueous. So, the salt water that we made, to link it up with things we've learned in previous units, we would have written that as NaCl aqueous. And the expression, if you wanted to think of it that way, is the salt, NaCl solid, plus the water, H2O liquid. Now this can be written as a chemical reaction per se, and I say that loosely because, as you know, dissolving is not a chemical change, and we'll write that down. Whoops. And I'll elaborate on this in a few more lessons. But just a reminder, this is how we could kind of write it as chemists, chemically. And just a reminder, dissolving is a physical change. Even though I wrote this expression as if it were a chemical reaction. So why is it that I can do that? Why can I write this as a chemical reaction, but it's not? It's a physical change. Well, it has to do with what's going on in our salt water. So again, let's try to zoom in and draw this with a little bit more detail. The salt is made up of a cation of sodium and an anion of chloride. And because it's an ionic bond, we have these cations and anions all attracted to each other in a 1-to-1 ratio in what's called a crystal lattice. Now I'm purposely using these two different colors to show you how this is all going to work at the end. I think you see where I'm going with this, so just to speed things up, I'm going to do all of my cations and then all of my remaining anions. And of course, I'm going to label it because my drawings are not so great. We have a crystalline solid. That's in our little scupula or our spoon in the picture that we have to the right. And I'm putting it into water. Water, we know, is a bent molecule where oxygen is our partial negative region and hydrogen is our partial positive region. And the reason why this solution is made, I'll change a different color. This solution is made because of the attractive forces between the salt and the water. The attractive force is one that you kids talked about a lot last unit, even though we didn't technically learn it in our states of matter unit. We were saving it for this one. It's the you're right, the ion dipole. Right? You've got the ion from the NaCl, and you've got your water molecule, which is polar, has that permanent dipole. The oxygen end is our partial negative, and the hydrogen ends are our partial positive. So what happens when this crystalline solid and this polar molecule of water come in contact with each other, the water molecules are now attracted to the crystalline solid. The oxygen end, because it is partially negatively charged, is going to be attracted to the positively charged sodium ions. And it's then going to detach the sodium ions from the crystalline solid and surround it. Let's draw what that will look like. So again, the sodium ion is a cation, positively charged, and it's going to get attracted to and surrounded by the oxygen end of water molecules. As you draw, pay close attention that only the oxygen end of the water molecule is facing the positively charged sodium ions. And conversely, the partial negative end or hydrogen ends of water are going to be attracted to the negative components in the crystalline solid, or the chloride ions. It's going to be attracted to the crystalline solid and then detach and surround the chloride ions. Let's draw that next. As we draw it this time, make sure to point the hydrogen ends of water facing the chloride ion. And again, that's because hydrogen is the partial positive part of the water molecule, and the partial positive end will be attracted to the negative ion. And there, my friends, are your ion dipole attractive forces, thus allowing the solution to be made. Lastly, there are some circumstances where solutions are not made, like oil and water. They never mix. And that's because they have no attractive forces between their particles. So how do we know if a solution will form? Well, chemists have a little slogan that we can use to help us remember. But our first explanation, I said it, but let's write it down. There has to be attraction between the solute and the solvent. So how is it that we can tell whether there's going to be attraction? It's this slogan, like dissolves like. So for example, we just said water will dissolve salt. Right? That's been our example this entire lecture. Water, we know, is a polar molecule. Whoops. It has dipole-dipole, London dispersion, dipole-dipole, and hydrogen bond forces. It is going to have the ability to dissolve salt, which we know has ionic forces. And even though it wasn't part of our example, because of the slogan, like dissolves like, it will be able to dissolve other polar molecules. Now, even though it has London dispersion forces, and so do nonpolar molecules, the dipole-dipole and hydrogen bond forces are so strong and so dominant that the London dispersion forces are outmatched. So it's not going to be able to dissolve oil. That brings us to our next one. So water will not dissolve oil. Well, again, we know water is a polar molecule. It's got the London dispersion and the dipole-dipole and the hydrogen bond forces, but it's not going to dissolve an oil. What does that tell us about the attractive forces of an oil? The only thing it's got going for it is London dispersion forces, and that's because it's a non-polar molecule, and our slogan is like dissolves like. So a polar molecule will not dissolve a nonpolar molecule because they are not similar. They are not alike. What will oil dissolve in? Well, it will dissolve in other nonpolar solvents. A classic example in your everyday life is carbon tetrachloride. This is what is used at dry cleaning places. Your dry cleaners are well known for being able to get stubborn stains out of your clothes. And that's most likely because the stain was caused by butter or grease or another kind of cooking oil. And again, oil won't dissolve in water, so water won't get that stain out. The dry cleaners, though, use a wet chemical. Your clothes do still get wet. They just don't get wet with water. They use a nonpolar solvent, such as carbon tetrachloride, and, excuse me, they are able then to dissolve the stain that is left on your clothing. Finally, the last category of chemicals that we need to talk about are alcohols. Alcohols are unique because they are a family of chemicals that have a polar and a nonpolar end. Let's write that down. They're a family of chemicals that have a polar and a nonpolar end. As a result, they can dissolve both polar and nonpolar solutes when they're the solvents, but they can't dissolve ionic solids. Let's write that down. They are able to dissolve polar and nonpolar solutes, but not ionic ones. The dipole forces in an alcohol are too weak to be able to attract and then detach the cations and the anions from the crystalline solids. From here, you will pause, or stop, I should say, and try the worksheet that's in Google Classroom, and then there is a lab demonstration for you to watch, and then take some data as you watch the video. So to summarize one more time, a solution is a homogeneous mixture. Homogeneous means the ratio of the components are uniform throughout. In other words, you take a sample from the top, the middle, and the bottom, and you will have an equal distribution or an equal ratio of the solute to the solvent in all three of those samples. The solute and the solvent are the two components to a solution. The substance being dissolved is the solute, and the substance doing the dissolving is the solvent. The whole reason why these solutions can be made is because there are attractive forces between the solute and the solvent. The attractive forces have to be similar, otherwise a solution or dissolving will not take place. Thanks so much for watching. Enjoy your practice problems. See you soon.